ஏதோ ஒரு ஃபீலிங்.
சார் பட்டன் வந்து சன்லைட்ல வச்சு பார்த்தாலே அதோட இது சன்லைட் தெரிஞ்சிருது சார்.
Okay, buttonல sunlight வச்சு பாத்தீங்க. Okay, so used sunlight. Say okay, very good.
Yes sir.
Okay, very good. Anybody else? How did you guys figure out safety pins? How did you guys figure out safety pin? Safety pin எப்படி கண்டுபிடிச்சீங்க? யார் safety pin ன்னு சொன்னது? We don't have a whole lot of time. And I would love to see you guys also. Whomsoever is doing the okay, you guys went silent on me. Yes. கேக்கலப்பா, கேக்கல தம்பி. Unmute பண்ணுங்கம்மா. And you got to unmute. You got to unmute. ஒன்னும் கேக்கலப்பா. கேக்கல தம்பி. All right, fair enough. I think, okay, in the interest of time, let's move on. So, இப்ப கேக்குது. Yes, now I can hear you. Yes.
சார் கேக்குதுங்களா?
கேக்குது தம்பி. சொல்லுங்க தம்பி.
அன்மியூட் பண்ணிட்டியா? அன்மியூட்.
கேக்குது தம்பி. சொல்லுங்க தம்பி.
சார்.
சொல்லுங்க தம்பி. கேக்குது.
சார் என் பேர் கோகுல் சார்.
சொல்லுங்க கோகுல். சொல்லுங்க கோகுல். I think we lost you. Wonderful. Let's get back to where we are. Gokul, I think I lost you, and that's okay. I think in the interest of time, let's move on. So that is the research, right? That is the research, right? Again, what we did was a very small activity, and if you have not figured out, you can still go back and then figure it out. I intend to do it for about 15 minutes, but we didn't have time. But that is the nature, right? So we have things that we don't see it, but we know it exists. But then we use our critical thinking, as I shared earlier. We use our critical thinking. You all observed and you try to see what it is. As somebody said, somebody felt it, right? That's a hypothesis, right? Somebody felt it, there was a marble, right? That is the hypothesis. You made the hypothesis and then you try to like move around up and down or whatever you did, right? Whatever you did, the experiment, whatever you did to confirm, and then you made a conclusion that it is a marble, right? That it is a இது வந்து கோலிகுண்டு அப்படினு நீங்க வந்து அத ஒரு क्वेश्चन பண்ணி ஒரு ஹைபோதசிஸ் பண்ணி அதுக்கு whatever the experiment கொடுத்த அந்த 10 நிமிஷத்துல experiment and then you are able to make a conclusion that these are the objects, right? This is the very general nature of any scientific research, right? But of course, things gets complicated. So where does the math comes into play, right? Math comes into play as a tool, right? For example, in the activity that we just did, we know you cannot have 10,000 pound or 10,000 kilogram items in that one because the box is very small. It can only be a small object, right? Anything that is inside has to be smaller than the volume of the box, right? So we know that for a fact because we know you can have a 10 square foot item inside that box, right? So these are the these are the observations that we kind of make from this. Just a minute, I think. Just hold on a minute. Let me just close my off. All right. So these are the so these are the observations that we made. I'm sure you can if I give you more time, you should be able to figure out a lot more things, right? So the most important thing is, in this one, that what I want you to observe, I'm sure some of you might know about this, it's called Bloom's taxonomy. There is a higher order critical thinking, right? There's an order for the critical thinking. There's an order for the learning. The lowest order is the remembering. And then second order is the next order is the understanding. Then whatever you remember, whatever you understand, you try to apply, and then you analyze, and then you evaluate, right? So what you did today, just now a moment ago, is you evaluated, and then you analyzed. You analyze things based on what you had in your hand, and then you try to evaluate, right? That's all we have. The highest order of learning is creating something. That is when you become an entrepreneur. That is when you become a scientist. That is when you create something new, right? That is when you're a scientist. That is when you're an inventor, right? That is the highest order of critical thinking. That is the highest order of learning. But that's so we use this to whatever that we learn. So the mathematics is a wonderful tool. Math is a wonderful tool to quantify many of these observations. Mathematics, as they say, it's a queen of all sciences, right? It's a wonderful tool to observe, wonderful tool to confirm, wonderful tool to verify whether certain things exist or not, right? But I don't want to get into that too much of time. But what I want you to do is I'm supposed to talk about differential equations. Let me get back to the differential equation. So where is this differential equation is going to come into play in mathematical modeling? And derivatives plays a vital role. And also equations plays a vital role. And that is the beauty of the mathematics, right? So can someone tell me, I think I'm going to ask one of the audiences, can someone come to the mic and say, what is the derivative from the, I'm sure you're all think I'm a layman, that I only studied, third grade, third standard. Assuming that I'm an uneducated person, I'm a farmer. How would you explain to me what the derivative is? Can someone tell me what the derivative is to a farmer? Can someone come to the mic and, what would you say if somebody asked you, what is the derivative? I know I looked at your syllabus. I know you all have taken, most of you might have definitely have taken differential equations, and even the master's students have taken differential equations. So PG students have taken differential equations. I know it's in your syllabus. I looked at your syllabus. So can someone tell me how can you explain a derivative to a farmer? And I saw your magazine. You have a lot of, go ahead. And introduce yourself.
Sir.
நீங்க இங்கிலீஷ்ல சொல்லணும் அவசியம் இல்ல, தமிழ்லயே சொல்லுங்க, பரவாயில்ல.
Sir, myself Praveen, sir. Myself Praveen.
Praveen. கேட்கலாமா? Rate of change. Okay, very good. Rate of change. Very good. இது ரேட் ஆஃப் சேஞ்ச்னா போய் நம்ம ஒரு விவசாயிட்ட சொன்னா அவங்களுக்கு ஒன்றும் புரியாது. அவங்களுக்கு எப்படி சொல்லுவீங்க? அவங்கள்ட்ட போய் எப்படி சொல்லுவீங்க? நான் களை எடுக்கிறவன், நாத்து நடுறவன், என்கிட்ட போய் நீங்க ரேட் ஆஃப் சேஞ்ச், நான் எனக்கு என்ன புரியும்? உழுகிறவன் நான் பார்த்தேன், உங்களுடைய மேகசினை பார்த்தேன். அதுல வந்து இந்த சிறுதானியங்களை பத்தி தான் நிறைய இருந்துச்சு. மில்லட்னு அங்கிங்கனாதபடி எங்கும் மில்லட்டா தான் இருந்துச்சு. அதனால உங்களுக்கு நல்லா தெரியும்னு நினைக்கிறேன். நீங்க வந்து ஐம் ஷூர் நிறைய பேருக்கு விவசாய பின்னணி இருக்கும்னு நினைக்கிறேன். விவசாய பின்னணி இல்லாட்டியும் அந்த விவசாயத்துல சார்ந்தவங்களும் நிறைய பேர் தெரிஞ்சிருக்கும்னு நினைக்கிறேன். உங்களுடைய மேகசினை பாக்குறப்ப அதனுடைய சாராம்சம். சோ ஒரு விவசாயிக்கு நீங்க எப்படி சொல்லுவீங்க? டெரிவேட்டிவ்னா என்னமோ படிக்கிறீங்க, டெரிவேட்டிவ்னா என்ன சொல்லுவீங்க அவன்கிட்ட? அவங்கள்ட்ட போய் என்ன சொல்லுவீங்க? என்ன மக்களே? Come on, we can do better. So in the interest of time, let's move on. So what is the derivative? As Karta Sunar, he said it already. It's rate of change, right? So it's about measuring a change, right? It is about அதாவது ஒரு தமிழ்ல சொல்லணும்னாக்க ஒரு மாற்றத்தை கணிக்க கூட ஒரு 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 கணிப்பானா எடுக்கணும் அப்படின்னா அது வந்து ஒரு எவ்வளவு மாற்றம் நிகழுது, எப்படி ஒரு விஷயங்கள் எப்படி மாறுது அப்படிங்கிறத மெஷர் பண்ணணும்னா அதுக்கு உண்டான சயின்டிஃபிக் measurement தான் derivatives அப்படிங்கிறது, right? It's about that is the rate of change, right? So மாற்றத்தை கணிக்கக்கூடிய ஒரு அளவீடு தான் வந்து டெரிவேட்டிவ், சரிங்களா? So now let's quickly I want to share something, then we will move on quickly on a derivative. So what I'm going to do will be based off of that. So the modeling that I'm going to do next, right, is going to be based off of that. I don't know why it's keep on doing this to me. Hold on. All right. You all can see what I see, right? So now let's take a look at this, right? You just said dy over dx, the symbol for the derivative, right? What you said? It's the rate of change, right? Suppose, let's just say, what does this mean? As I said, as you see earlier, if this is your f, and I want to measure the change from this point to this point of this function, right? What we do is, as the x changes from here to here, we wanted to see how the y changes, right? So this is what they say, you know, in I don't know, in the United States, people say it's the rise over run. What is the meaning of rise over run? So if you take a look at this guy, this is what they call run. How much you go from point A to point B, and then this is the rise. So change in the y is the rise, because it's the y-axis, and change in the x-axis is the run, because that's in the x-axis, and this is what they say, it is the derivative. Right? That's what they say, that is the derivative. Right? Now, so that is what we denoted by dy over dx. Right? That is what we said in, so basically change in y due to the change in x, right? How y is changing, or how much y is changing when x is changing, is what is the essence of the derivative, right? So suppose if I say the change in y with respect to change in x is exactly same as the y, right? How do I measure that, right? What do I get from there, right? What would I get from there is, so suppose let me take a look at this y-axis. Let me take a look at this x-axis. Let's say I have a point right here. This point is, let's just say 1, 1. That means x is 1 and y is 1, right? By the way, you all can see me, right? You all can see what I see, what I'm writing. Can someone give me a thumbs up? I can see you. So can somebody give me the thumbs up? Thank you, appreciate it. So now, here the x value is 1 and the y value is 1. I am right here. So this tells me, since the y value is 1, at this particular point, the change that is going to happen is also going to be 1. What does that mean? Whenever I move 1 unit in the x-axis, I have to move 1 unit in the y-axis, right? So if I want to move, so at this point, if I'm right here, this differential equation dictates me that if I'm right here, the only way that I can move out, the only way I'm supposed to move, if I follow this differential equation, is to move up. 1 unit to the left would make it 1 unit to the up, right? So I am right here now. Now that I'm here, my values are now 2, 2. If I'm 2, 2, right? If this is 2, 2, my y value is 2. So therefore, if I'm right here, how am I supposed to move up? For every 1 unit that I move on the x-axis, I'm supposed to move 2 units on the y-axis. As I said before, right? This is 2. Rise over run is 2, right? Rise over run is 2. So I'm supposed to move 2 units for 1 unit in the x-axis, right? So if I do that, then what do I get is, I get from right here, for 1 unit, I have to move 2 units up. I'm right there. I'm discretizing here, by the way. I'm just making it very simple, right? And then if I'm right here, my point is, this is 3, 4. X is 3, Y is 4. Now that means for every unit that I move up, I'm supposed to move, for every unit that I move to the right, I'm supposed to move 4 units to the up. So it's going to be 1, 2, 3, 4. So excuse my illegibility, right? So if I keep on do that, I get a curve. It's a 0, right? I get a curve something like that. And can someone tell me what kind of curve this is? Can someone tell me what kind of curve this is? No? Yes? Can some students come and tell me what kind of curve this is?
Sir,
Yes.
sir, 7,5.
7,5, yes. So what kind of curve in the graph in the equation mari irukku?
Sir,
So what kind of graph is this? What does it look like?
புரியல.
Parabola?
Sir,
More than a parabola, right? Let's just say my left side is my left hand side is this way, right? What kind of graph is this? What kind of graph is this? I'll give you a hint. When you take the derivative, it doesn't change. When you integrate, it doesn't change.
sir,
What is the function that doesn't change when you do the derivative?
exponential.
Exponential. Very good. Thank you. That's what this is, right? It says when you do the derivative of the function remains the same. And what function is that? The derivative is exactly same as the function, correct? And what function is that? That function would be e to the x, right? And by the way, this is called the, for those who have taken some advanced math courses, this is called the direction field. This is called the direction field, by the way. But anyway, the point what we are trying to do is, now if I know the change, how the change is changing, right? How the change is happening, then I can figure out the dynamics, right? Suppose, let's just say this is the population, this is the growth of some sort of a virus, right? Let's just say this is the growth of cancer, right? So the cancer growth rate is same as what it is, and you can see the cancer is growing very fast, right? That's not good, right? That is not good. If the cancer is growing very fast, that is going to be very detrimental, in some cases fatal or deadly to the patients, right? So now let's take a look. Now that we have done this, right? Let's do a small experiment. I don't know how we are going to do, but I think I'm going to do a small experiment to see how the mathematical modeling works, right? Let's just do a small experiment. Where am I right now? Okay. So let's do a population dynamics model, right? Some very, very simple, very basic population dynamics model. Let's do that. what I'm going to do is, we have to make assumptions when we do some mathematical modeling, right? We have to make some assumptions. There is a wonderful book called Spherical Cow. You should read it. It's a very comical book. It's not only for math people, it's also for physics people. Mathematicians always assume things, right? Mathematicians always assume things. So I'm sure, if I ask Professor Anis Fatima, she's a topologist, right? If I ask her what is how would she describe a cow, she would say the cow is pretty much same as ellipsoid, right? Or because I think she would find a morphology or some sort of isomorphism between cow and even a sphere. As far as the mathematicians are concerned, we don't care if it's a cow or if it's a sphere. For us, it's both the same, especially for the topologists, it's both the same. So we're going to do something very similar. So what we have is I think I'm going to ask some of you to come to the front or to come to the table wherever you are, right? So we're going to do some small experiments to how to do this mathematical modeling, right? So what we are going to do is, let's just say we have a fish population. Let's assume we have fish populations. The buttons are the fish, right? Buttons are the fish. So now what we are going to do, I want 2 or 3 volunteers to the front, 2 or 3 volunteers to the front. You will have, let's just say 50 buttons, right? You will have 50 buttons. I want you to shuffle the buttons and I want you to put it on the table or on the floor. The one that is upside down like these are the dead, right? These are dead fish, right? Think of these are dead fish, right? Remember, we just made the buttons are our fish, right? Buttons are our fish. Ones that are not upside down are alive. I don't know what kind of buttons you have, and I hope you have these buttons. Maybe if you have different buttons, and that's okay, right? Again, we all make assumptions. That's perfectly fine. So I want you to shuffle, and I want you to start with the 50, and I want you to tell me the count. Is the instruction clear? I just want 2 people or 3 people at most. 2 is good enough. 3 is plenty. Come to the front, and I want you to do this experiment. I want you to do this mathematical modeling, and we're going to model this mathematically, and we're going to do some cool stuff with it, right? We're going to do some computational tools with it and to figure out all this. So can I have 2 people? Can I have 2 volunteers? All right, so what I'm going to do, I'm going to go to my Excel sheet one more time. Where am I right now? All right, so now we're going to do the first iteration. So we're going to have the population, I'm going to say P, population at 0, P0, right? I'm going to say U. U is the density, let's just say U0. Iteration, I know we have 50 fish. Let's just say for time being, it's a fish. We call each button as a fish, right? We'll change it later. Now tell me, can you shuffle and tell me how much you got after the first iteration? So I want you to shuffle, and I want you to count the non-dead fish, right? Fishes are the buttons. The buttons that are upside down, we don't count them. They are dead fish, right? The buttons that are straight, right? Tell me how many you are left. Tell me how much you got. How many we got?
Sir, 6 alive.
Only 6 alive out of 50. How many you start with? How many you start with? How many you started with? Mathematically does not make sense. It's a very skewed population. It's a very bad population. You're not feeding the fish properly. You're not giving them resources. You're making them die so quick. If you start with 50, you would not have 6. My math friends, especially my stats and the probability friends would say, oh, it should be 25. Close to 25.
Sir, 24 alive.
24 alive. See, that makes sense. Okay. Now take the 24 and do it one more time for me, please.
What is 24? 14.
14, okay, sounds fair. Let's do U3 one more time. After the third iteration.
7.
7. Oh, very good. Oh boy, very good. Okay, you 4.
Sir, 3.
3. Okay. You 5.
Sir, 1.
1. Okay. Let's see if this is going to survive or not. Is that fish a survivor? Did survive or dead? One more? I can't hear you. What happened? What happened? Dead? Can I say 0? All right. In the interest of time, I'm going to say 0. Okay? Is it okay?
Yes, sir.
Okay, wonderful. Now, what he just did is, mathematically speaking, so what happened? What happened in reality? Don't leave, just stay there, because we're going to do one more. We're going to do a few more, right? What we just did is the rate of change. If you think from the a priori estimate, mathematical perspective, modeling perspective, what happened is we expect, because when you roll a dice, when you roll a coin, you know that there's a 50% chance it's going to be on one side and 50% chance it's going to be on the other side, right? So we expect mathematically, using probability, that every step, every iteration, only 50% will survive, right? And that's what just happened. Of course, in reality, it's exactly not the same. So we start with 50, then went down to 24. We expected 25 and then 12, but then a little bit more. But the next time it's 50%, then less than 50%, then less than 50%, eventually dead, right? So if this is the cow population, you don't want this to die, right? So what do you do then? You know, in the olden days, when I was a kid, in all the lorries and all the buses, they'll say, Naam irvar, namak irvar. Right? I think they started with the Naam irvar, namak irvar, and then they say Naam irvar, namak kurvar, right? So now what I want you to do is I want you to repeat this same experiment, maybe the same people or maybe a different people. So what I want you to do at every single step, what I want you to do is at every single step, add 5 back. So whatever you have, shuffle it, right? And let's go with the Naam irvar, or Naam irvar, namak kurvar, right? So that means if 24 of them survive, add 12 to it, right? Add 50% to it. Can you know what I'm saying, right? Add 50% to it. Let's do that. Let's repeat the process. By the way, how am I doing with the time? How am I doing with the time? Am I doing okay? Or am I doing too long? I also need to run back home. Can you guys hear me okay? What do you got? I know it's a long day. I get that.
Sir, within 5 minutes, sir.
So finish it in 5 minutes?
Sir, within 5 minutes, sir.
Can you finish? You want to complete it in 5 minutes?
Yes, sir.
Okay. Okay, 5 minutes is going to be a little bit harder, but I'll try my best because I didn't even get to what I wanted to get to. All right, so now, in the interest of time, let's not worry about it. So now if I do this, right, what is the differential equation that I'm going to have? If I do this, the differential equation that I'm going to have for this one is, what has happened here is the following. Let me just share. I'll repeat this at some other time. Oh, man. Every time. So what just happened is the following. So every time the change, right? The rate of change, the change of the population, I'm going to call it as the population as the U. U is the population, in this case, is the fish population with respect to time, du over dt, right? Du over dt is basically speaking it's dying, right? It's going down. Every single time it's going down. So it's a negative. The change is negative. How much? Whatever the initial population is, half of it. Half of what the Y was. More precisely, I'm going to say 1/2 times the Y. Right? So what we have, what we just did, right? If I model this mathematically, what I would get is the differential equation where the rate of change of the population with respect to the time is negative half of what the original population is. That's what just happened. We just witnessed it, right? Now that I have this equation, I don't have to run this, right? I can use, now we have a lot of computational tools. I can use a whole bunch of computational tools, which I'm going to show you in a moment. I'm sure you all know how to solve this. I will let you solve this, but I'm going to show some cool trick. So I'm going to share some my Python code. Let's see. You all can see the Jupyter Lab, right? By the way, I'll share where you can find the code. So I'm just running this. So what we have is, we have this differential equation. That's a differential equation we have. That is the differential equation that we have. I wrote it in terms of dy over dx. And here's the Python code for this, right? If I run the code, as you can see, if I start with we start with the 50, correct? So initial value is 50. When I start with 50, it eventually dies down, right? If this is the fish population, we don't want that to happen. If this is the cow population, we don't want that to happen. But if this is the cancer, we want this to happen, right? So now, what I want to do, I want to add. We don't have time. I wish I could do the experiment. I'll let you go home, or whenever you're free time, try to do this. I want to add every time 5 fishes back, right? I want to add 5 buttons back to my equation, and I want to do this by adding. At the end of every iteration, at the end of every shuffling, I want to add 5 more, right? When I add 5 more, what happens? Let's take a look, right? So if I'm going to add 5 more, and the same thing when I do, what happened? You see, there is an equilibrium that the fish is not dying anymore, right? There's now actually you would expect there's going to be 5 left. But actually, that's a very interesting thing, but you can go home and do that. If you go home and do that, you would see there's always the number of buttons that will be on the top, or the number of fish in this case would be always 10. Since I'm adding 5 every time, there's going to be always 10. If I add, let's just say 10 every single time, right? After the shuffle, you add 10 back, right? This is called immigration. You add 10 back, and now you see it's going to go to 20, right? And that's because I started with the population 50. What if I start with the population 5? I start with 5, still I went back to 20. Let me start with 1. I still went back to 20, right? So now if I'm adding 5 fish, or 10 fish in this case, at every single iteration, what happens is my population now settles, right? There's an equilibrium. I'm sure those who have taken autonomous differential equations or a phase plane and phase line, right? Equilibrium points and so on, you would know what I'm talking about. If not, you're going to learn them, right, in your courses, and you will see no matter where I start, it is going to reach the equilibrium of 20. Right? It is going to reach the equilibrium of 20. So we can model the real world scenario using these differential equations. Again, I don't have too much of time, so in the interest of time, I'm not going to spend too much of this. But I will, if you want to look at this code, you can go to my YouTube channel. I think if you go to, let me quickly share, you can go to my YouTube channel. Just search Professor Jafar Ali. And right there's the YouTube channel. You can find the code somewhere here. Where are my videos? You can find the code right here. Right? Here is the code. If you want to go back and, I'll let you go back and play with the code, and you can do all kind of cool stuff, right? Again, these are all free sources. Python is a free source, so you have no excuse not to learn it, right? Again, these are computational tools are very, very important. So make sure you learn them. Now let's get back to our presentation. Let's see where we are. So now that is the basic model that we can do. So what I want you to share today is the is one of my work on tumor growth, on cancer, with one of my undergraduate student, UG student. Actually, she's not only a UG student, she's also my, in the United States, there's something called dual degree, where 11th grade students, right? 11th grade students, if you're good enough, you can attend colleges, and the fees will be paid by the school district, So she came to my she was a very smart kid. She came to my class, my calculus, when she was in 11th grade. Technically, she was 11th grade student, basically plus one, Tamil plus one student. She came to me during that time, and then she did some research with me. It's a very simple differential equation research, but she did very well. So I want to quickly talk about this. And she is Samantha, and she's doing very well now. She got into the top. There's something called Ivy League schools. You can Google later. It's called Ivy League, the best 10 schools in the entire world, right? That is where Harvard, that is where MIT, University of Pennsylvania, Yale, Columbia, all the top school in the entire world, right? She applied to, I think, 6 of them. She got into all 5 of them. She got admitted into the MIT. She got admitted into the Yale. She got admitted into the Columbia. She got admitted to the University of UPenn, University of Pennsylvania. She chose University of Pennsylvania eventually, but she didn't. She got admitted into MIT, and she said no to MIT. Right? She's a very smart kid. She's a very, very dedicated, hardworking kid. And this is the research with her. Again, technically she's a high school student at that time when she was doing the research with me. So I thought I will share this with you. Right. So what we did, we looked at what is called the ontogenic growth. Ontogenic growth is basically like you look at any organism from the birth to until the maturity, until pretty much the end of the lifespan, right? And that is called the ontogenic growth. And if you look at the growth, usually the growths are something like this. So if you look at this, right, here's what you see, that this is the graph of a growth of a guinea pig. Here is when it is born, and then this is the juvenile, and this is the kind of like adolescent, and this is the mature state, right? That's a guinea pig right there. And then if you look at the guppy is the fish, right? Again, that is also has a similar structure. If you look at the hen, that also has a similar structure. I know we all like a jallikattu, we all like, cow, right? If you look at the cow also has this structure. So if you look at any organism, the growth is usually something like this. So it grows in some sense very fast at the beginning, and then it reaches some sort of a maturity. Once it reaches the maturity, it stays right there, right? That is the natural ontogenic growth of any organisms, right? And here are some more data there. But if you look at, so if you try to normalize any of these graph, you will see this kind of a growth right there. So for our purposes, we are interested in finding the growth of cancer, right? Growth of a cancer cells in a human body. Again, I don't have too much of time to get into the details. So what happens? There's a paper in Nature. Nature is one of the top journals in the world. It's called Nature, and there's a paper by there's a research article by West, Brown, and Enquist, and they say the tumor growth has this particular that's a tumor growth, by the way, has this particular equation. So here's the equation. This is the tumor growth. M is the mass of the tumor, and it follows this particular differential equation. So we looked into it, and our goal was to, what if I give a medicine, right? What if we give a medicine? Can we, and if you take a look at the growth, this grows also kind of like similar to the growth that we had, any ontogenic growth. So our goal is to, how do I stop the growth, right? If I stop the growth means I have a differential equation right here. If I put a minus C, that means what am I doing? If I subtract something from this growth, that means I am stopping the growth, right? I am stopping the growth. So that's called harvesting, harvesting models. So in our case, it's going to be a cure model. The curing model would be, what if I put a negative C, a constant dosage of medicine? What is going to happen to that? The idea is to figure out an optimum level of medicine so that we don't overdose the people. We don't overdose the patients, so that it's healthy enough for them. There are no side effects, or we will have minimal side effects. At the same time, it can cure the medicine. It can cure the patients with the cancer, and that is what we looked at. And so here's the term right there. That is the du over dt. and we generalized it with this P, and this is the treatment term right there. That is the treatment term, minus C, as you can see right here, right? That is the treatment term right there. And then I hope you all can see what I'm seeing. So let's take a look. I think I'll share my, just a minute, let me share my iPad so you can see better. How am I doing with the time? Another 5 minutes is okay?
Okay, sir.
Okay, all right. So I'll finish it in 5 minutes, right? So as you can see right here, so here is that treatment term right there. Here is the treatment term, C, right there. I also need to run back. So if I put a minus C, that means I am kind of stopping the growth. This is the growth of, in this case, a tumor. In this case, the tumor cells, cancer cells. If I put a minus C, that means I am changing, or I'm reducing, I'm lowering the rate of change of the growth. So when that happens, we ran a couple of simulations, right? And we do that. And this is again a very basic one-dimensional ordinary differential equation. You can extend this to a high dimensional case, and that is when all the PDEs comes into play. We add a diffusion. And again, this is called the reaction diffusion systems. I have a lot of stories I can share, but I don't have time. Maybe another time I will be happy to share. So here's the diffusion system, and here is the reaction term. So that is how things change. When you try to solve this, things get a little bit tricky. But I do have a paper where we were able to solve with the harvesting there. So when she ran with just this ODE, ordinary differential equation, and then we were able to do some numerical simulation. As a matter of fact, some of my students, another set of students, David Bryce, Elliot, and Brian, what they did, they wrote a Java code. So what do? They looked at the X-rays of brain tumor, and then they ran it through this system. They created this software. They ran it through the system, and then based on looking at the slices of the X-rays, MRI in this case, by the way, set of X-rays, we can compute the tumor volume, right? Again, using just like our, in calculus 2, I don't know where you learn them. We try to find the volume using disk method and so on. So they use that method to figure out the volume of the tumor. And then so they have this data from MRI from one of our local hospital. So they try to figure out, and then they try to see what happens to when we try to apply this to this model, what happens. And as you can see, when you give too much of medicine, this can really go down really fast. So we were able to extrapolate it. So we ran this. So for various different the term C, and this is with the C being almost 0, that the growth reached this level. And then this is as you can see, kind of lower it down. And this is where you can see kind of like where you have this model, right? And what happens, and a very important thing that happens when you do this, right? Especially when you deal with the cancer, what you want to happen is the following. And what we observed is a very interesting thing. So let me show you, and then I will call it today. So here is the tumor growth, right? Here is the graph of the tumor, the mass of the cancer cells growth. What happens is this green zone is where it's safe. As long as if you can contain the tumor growth in the green zone, that means the patient can survive, right? But if they reach beyond that level, then that is deadly, and that is going to have an impact on the patients, and it's sometimes it can be deadly, right? Now, here is the natural tumor growth. If you don't treat the tumor, the patient will reach this stage. I think when they reach this particular stage, very likely they're not going to be surviving, right? They're going to be probably going to go through a whole lot of miserable time. So now what we want to do, we want to treat them. We want to treat them. The best thing for our scenario would be, people might not even detect they have a cancer until they reach this particular point. So then they realize they have a cancer when they reach here. We want to start treating the patient at this particular point, and the goal is to eventually bring it down, right? We want to eventually bring the mass of the tumor, mass of the cancer to this level, and that is our goal, right? But in reality, that doesn't happen, right? So what sometimes happens is the following: you get something like this, right? So what do? You detect right here. You detect right here the patient has a cancer, you treat them with a low dosage, it comes down, and what worries is after some time it goes back up, right? That's called relapse. They say it's called relapse. So the relapse is a very dangerous thing, because then if you don't treat the relapse very well, if you don't take care of it very well, what can happen is that it can go back, and then it can go reach the level 3 or level 4 deadly level, and that's bad, right? But is there a way that we can tell the patient, don't worry about it, if you continue to keep this level, you may have oscillations, something like that can go up and down. You may have oscillation, something it can go up and down, but eventually will reach this level. The idea is to minimize the amount of dosage, minimize the amount of medicine, so that you don't have side effects. Those who go through cancer, you all know, when they go through chemotherapy, they all lose the hair. The body goes through the entire transformation, right? It's not sometimes not really good, so it changes. So it's very, very important to lower the dosage or to lower the treatment intensity as low as possible, to the extent we can still treat the patient, we can still recover the patient, and we were able to do something like that. And then wonderfully, and this is the data that they try to, and whatever, this is the model that we got, by the way, as I've seen earlier. This is the kind of the model that we got using our numerical simulation, using purely simple differential equations model, right? We were able to get this, and then that was corroborated. With the data from some of those mice. I think they had some data right there, so they had the mice over there, and they were able to do that. And so that was very interesting, that observation, that again, the idea is to use simply mathematics, right? The beauty of the mathematics to model something that even we don't know what's going to happen, but we can predict, right? Or not necessarily predict exactly and precisely, but we're able to predict something that is very similar what can happen. And that's a wonderful tool, and that's a beautiful tool that we could do. And again, as I said, this plays a vital role over there. I think I'm going to skip all this. Of course, you can do this in elliptic PDE. If you are doing if you're a researcher working on elliptic differential equations, here are some elliptic reaction diffusion systems where we can do that. And here is actually a higher dimensional elliptic PDE. And then I was able to prove that for a set some sort of harvesting, this will have a unique, not unique, it will have a positive solutions. And we are able to do that for some of these things, and we use the method called sub and super solution. I don't have time, I'll stop it right here. So if you have time, I'll be happy to answer any questions. And I think I'll stop it right here and answer any questions that you may have. I know it took a while, and I'm sorry, maybe another time. When I come there, I'll be happy to maybe share most of the things. I will stop it right here. And again, I want to thank the organizers once more time, and I especially want to thank Professor Anis Fatima. She came and asked me through a friend of mine, and I don't think I had given a talk. I had given a talk at 3:30 my time. This is my first time. I've given a talk internationally in multiple times in multiple places, including in India, Europe, Middle East, in all over the place. But I don't think I've ever done a talk at 3:30. But Dr. Anis Fatima, my mom's name is Fatima, right? My mother name is Fatima. So it's very hard for me to say no to her. Maybe because I don't know. I feel like emotionally connected with the name. So she's like she's like a kind of like a motherly kind of a figure for me now. So I think I said yes to her, and I hope it is worth it. And I hope that you all had a good time. You all are able to appreciate, and you all be able to enjoy the journey of this talk. So I will stop it right here, and I'll be happy to answer any question that you may have. Any questions? And I know I'm the guy between you and your dinner. I'm the guy, I know you're waiting for your bus. I know some of you might have lost your bus. Some of you are like missed your bus already. You're waiting, what is the next and so on. If I made you late, I'm sorry. And especially for those who are trying to break the fast, I don't know how many of you are there who need to break the fast. I also need to go and eat so that I don't miss my breakfast for the fasting as well. So if that is the case, then I apologize in advance, and I hope it is worth it. Dr. Anis Fatima, any questions for me from the students? கேளுங்க எனக்கு தமிழ் நீங்க இங்கிலீஷ்ல கூட கேட்க தேவையில்லை, தமிழ்லயே கூட கேட்கலாம். I'll be happy to answer any questions you have. I feel like I'm the only guy who's talking. Hope you all okay. Any questions?
Hello, sir.
Yes, ma'am.
சார் ஒவ்வொரு சிச்சுவேஷனுக்கும் அந்த ஃபேக்டர்ஸ் நிறைய ஃபேக்டர்ஸ் இருக்கு. எப்படி சார் அதை வந்து நம்ம இவ்வளோ ஃபேக்டர்ஸ் தான் வந்து நம்ம டிஃபைன் பண்ணணும்னு எப்படி டிஃபைன் பண்றது ஒரு ப்ராப்ளம்க்கு?
Very good question. As I said earlier, we make assumptions. We make ton of assumptions, right? So we take sometimes we so the parameters also the more parameters that you add, right? It makes the problem more harder to solve. So we take one step at a time. We take one step at a time and figure out what is significant and what is the most significant and what is less significant. So we try to take a look at the most significant factor first, and we try to solve. And then we add layers, multiple layers of other models. So the very first models are, we take what we think is the most significant, and then sometimes we think it's significant, it may not be significant, and that's okay. But then that is how we kind of add layers one or the other, and sometimes we are successful, sometimes we're not successful, but we got to start something somewhere. So no matter what the problem is, as they say in English, how do you eat an elephant, right? You say one bite at a time. The Tamil English பொதுவா சொல்லுவாங்க, ஒரு யானை எப்படி சாப்பிடுறது, யானை வந்து ஒரு கடியா கடிச்சா யானையும் சாப்பிடலாம் அப்படிம்பாங்க. அந்த மாதிரி we still have to start something somewhere. We got to start with every single step. I think not necessarily the first model is going to be the best model, but that first model is the model that is going to help us to reach the next level. I mean, I'll just give you a quick example. In a iPhone, Android phone, everything, 20 years ago, the phone that we had was different. Like, I'm sure ஒரு நம்பர் அப்படியே ரவுண்ட் பண்ணி நம்பரை வந்து சுத்தி விட்டு ஃபோன் பண்ணோம். அது போய் இன்னைக்கு வந்து we have 20 years later, we have added multiple layers, and today we have a very smart phone that can do a whole host of stuff, right? So அந்த மாதிரி வந்து we have to start something somewhere, with the hope that eventually we're able to figure out all the other parameters, all the other layers. That is the usual attitude of scientists and anybody who does the mathematical modeling. Thank you, Ms. Hamida Beg. எனக்கு ஒன்றும் கேட்கல. I can't hear you. I cannot hear any of you. And I will say this, and I will say this, especially நீங்க வந்து I feel like உங்களோட டாக் கொடுக்கறதுல எனக்கு ரொம்ப மட்டற்ற மகிழ்ச்சி. ஏன்னா உங்களை நான் என்னையா பார்க்குறேன். நான் படிக்கிற காலத்தில் எப்படி இருந்தனோ நீங்கள் அப்படி தான் இருக்கிறீங்க. நானும் வந்து ஒரு கிராமத்தை சேர்ந்தவன் தான். இன்னும் சொல்லப்போனால் நானும் ஒரு விவசாய குடும்பத்தை சேர்ந்தவன் தான். நான் படித்தது வந்து ஊராட்சி ஒன்றிய துவக்கப்பள்ளின்னு சிவகங்கை மாவட்டத்தில் காரைக்குடியில் கல்லல் ஊராட்சி ஒன்றிய துவக்கப்பள்ளியில் தான் வந்து 4வது வரைக்கும் படித்தேன். நான் தமிழ் மீடியம் தான் படித்தேன். 10வது வரைக்கும் நான் தமிழ் மீடியம் தான் படித்தேன். நான் நாற்று நட்டுருக்கேன், களை எடுத்துருக்கிறேன், மாடு மேய்ச்சிருக்கிறேன், போய் கூட்டுறவில் போய் வந்து பால் கறந்துருக்கிறேன். அப்படிங்கிறப்ப உங்களை பார்க்குறப்ப, அதுவும் வந்து நீ எல்லாம் வந்து நிறைய விவசாய குடும்பத்தை விவசாயம் சார்ந்த சமூகத்தில் இருக்கிறதுனால உங்களை பார்க்குறப்ப என்னையை பார்க்குற மாதிரியான ஒரு உணர்வு இருக்குது. ஸோ உங்களோட பேசுனதில் இந்த இதுன்றதில் எனக்கு ரொம்ப ரொம்ப மகிழ்ச்சி, ரொம்ப சந்தோஷம். நான் ஒன்று சொல்லிக்கிறேன். நிறைய பேர் இருப்பீங்க, நம்மளால் வந்து படிக்க முடியாது, படிக்கிறது வந்து வெறும் வந்து இங்கிலீஷ் மீடியம் படிக்கிறவங்க தான், இல்லை ப்ரைவேட் ஸ்கூலில் படிக்கிறவங்க தான் வந்து படித்து பெரிய ஆள் ஆகலாம் அப்படின்னு நினைப்பீங்க. அதெல்லாம் கிடையவே கிடையாது. எல்லாராலையும் படிக்க முடியும். நம்பர் 1. நம்பர் 2, உங்களுடைய பொருளாதார சூழல் என்ன சூழலாக இருந்தாலும் சரி, கல்வி மட்டும்தான். இப்போ எஸ்பெஷலி வந்து பொருளாதாரத்தில் பின்தங்கி இருக்கிறவங்களுக்கு நான் சொல்லிக்கிறது என்னன்னாக்க, கல்வி மட்டும்தான் அவங்களை உயர்த்தும். கல்வி மட்டும்தான் என்னை உயர்த்தி இருக்கு. கல்வி மட்டும்தான் நம்மளை உயர்த்தும். அதனால வந்து கல்வியை வந்து எஸ்பெஷலி வந்து அதாவது வந்து மிகவும் கஷ்டப்படுற சூழல் இருக்கவங்களுக்கு சொல்லிக்கிறேன், கல்வியை விட்டுறாதீங்க. கல்வி நம்ம வந்து
So vote of thanks, sir.
Thank you, ma'am.
Good morning, sir. Good morning only for you, sir. And good afternoon to one and all present here. On behalf of the organizing committee of IWMMDE 2025 and my own behalf, I would like to extend our heartfelt gratitude for graciously accepting our invitation to be the chief guest of our IWMMDE 2024. Your presence at the workshop has been a tremendous honor for us, and we are deeply grateful for the time you take out of your busy schedule in join with us. Your participation has not only added prestige to our event, but also provided our students and participants with a unique opportunity to learn from your experiences and expertise in applying mathematical modeling and differential equations to real-world problems. And we are confident that it will have a lasting impact on their research endeavors. As a token of our appreciation, we presented an honorarium to our esteemed chief guest, Dr. S. Jaffer, sir, who, in a generous display of goodwill, graciously donated the entire amount to support the educational initiatives of our students. Thank you, sir. Once again, we would like to express our sincere gratitude for your support and participation in IWMMDE 2024. We hope that you have enjoyed your time with us, and we look forward to future collaborations, sir. Thank you. Thank you very much, sir.
Thank you. And I'm sorry I have to eat banana because I have only 4 minutes for my fasting. Okay,
sir. Okay, sir.
So excuse me. And again, I want to thank you and I appreciate it. ரொம்ப சந்தோஷம் வந்ததுக்கு ரொம்ப சந்தோஷம். And again, I think, as I said, நான் இங்கேயும் சொல்லிக்கிறேன், அதாவது தேவையுள்ள மாணவர்களுக்கு எஸ்பெஷலி வந்து நானும் ஒரு காலத்தில் கஷ்டப்பட்டவன் தான். நானும் ஸ்காலர்ஷிப்பே வளர்ந்தவன் தான். நானும் எனக்கு வந்து வீட்டில் எல்லாம் பெருசாக பொருளாதார உதவி இல்லை. ஸ்காலர்ஷிப்பில் தான் நான் வந்து படித்தேன், ஸ்காலர்ஷிப்பில் தான் நான் வளர்ந்தேன், ஸ்காலர்ஷிப்பில் தான் வந்து இங்கே வரைக்கும் வந்திருக்கிறேன். ஸோ அதனால் வந்து நீங்கள் கொடுக்குற அந்த ஹானரேரியத்தை தேவையுள்ள மாணவர்களுக்கு கொடுங்க. அவங்க புக்குக்காகவோ ஃபீஸுக்காக வாட் எவர் இட் இஸ், இஃப் இட் ஹெல்ப்ஸ் them to be a better in academics, if it in their life, please share that. I'll be that's my request, that's my humble request, and that's one thing that will make me happy, and that is one thing that will make me awesome. Thank you.
Thank you, sir. Thank you very much, sir.